recap, this is part 3 of a series of videos I've made about an unreleased app I was working on last year called FlipStream. While this video stands alone, you might want to check out the previous videos in this series before watching this one for more context. FlipStream is a cross-platform mobile app built using Apache Cordova for the front end. The back end is a RESTful API built on top of the Apache CouchDB NoSQL server. A quick intro to CouchDB if you're not already familiar. It manages its data using plain JSON documents, as opposed to MongoDB, which uses BSON. All operations are performed using standard HTTP requests with RESTful HTTP verb semantics. Bonus fun fact, it's written in Erlang. If you're not already familiar with functional programming concepts, learning at least the basics can definitely help your procedural or object-oriented programming efforts. Let's jump right into our API definition. The first thing I always do when defining a new REST interface is identify the nouns that need to be managed. If you've been with me since part 1 of this series, you might remember that I identified 2 nouns that I needed to track. Learner, which represents someone using the application to create or review flashcards, and card, which represents a flashcard. There's also an implied noun that must be included in any system that identifies people who are using it. To simplify talking about authentication and authorization, I'll be referring to learners as users for the rest of this discussion. As a quick refresher, a CouchDB instance supports multiple databases. Each database stores a collection of JSON documents that are uniquely identified by their ID fields. Deciding how to structure your document IDs is actually a big deal that will impact your application for the rest of its life. Hint: sequential integers are not a good idea for numerous reasons. So what is a good document ID scheme? The type:"id" method is so ubiquitous that it's used to support database partitioning as of CouchDB version 3.0. It's simple, descriptive, and dry. Object types should be simple one-word tokens. Within each object type, the unique IDs should be chosen to make common operations easy to perform without additional document lookups. For user objects, the user's email address is unique and persistent. For new flashcards, a Unix-style create timestamp is sufficiently unique. It also provides the ability to do some rudimentary sorting without the need to index or look at the document contents. Now, let's talk about CRUD. CRUD is one of those acronyms that sticks with you throughout your career. When developing any system that manages data, we need to think about how we will create, read, update, and delete that data. In the case of CouchDB, these 4 operations map cleanly to 4 standard HTTP verbs: put, get, post, and delete. So, for example, this GET request will return the current JSON for the card. Post and delete to the same URL support updating and deleting the document, respectively. This is about as simple as it gets. Unfortunately, for a real application that will be released into the wilds of the internet, it's a little too simple. In the real world, malicious users exist. To prevent them from accessing data they shouldn't or from modifying things that don't belong to them, we need to support 2 major functions: authentication, i.e., who are you, and authorization, what are you allowed to do. CouchDB only supports 2 classes of users, admin and normal, and as for access control, it supports global document read and write on a per-user basis. As clean as the basic CouchDB REST interface is, we need to put something in front of it. The thing we need is a reverse-proxy server. It will allow us to look at every request going in and out of the CouchDB server, authorize our users, validate requests, and massage response payloads any way we please. There are a lot of FOSS reverse proxy servers that you can put in front of CouchDB that will work out of the box. While they're great for providing more robust authentication, load balancing, etc., they don't really solve the problems we need to solve. So let's walk through a simple request and see what functionality we need. This is a basic post request to update a given flashcard. The public API exposes a simple /type/unique ID URL structure. We don't and shouldn't expose the underlying CouchDB database name to the outside world, so the first hook we need is a URL processing hook. The URL hook allows our code to translate the incoming URL from our chosen API scheme to the CouchDB URL space. It also provides an opportunity to do session management before other handlers are called. The pre-hook is called just before the request is forwarded to the CouchDB server. For read-only requests, there isn't much to do, but in the case of updates like this post request, this hook allows us to validate the contents of the request, add any system-specific metadata we need, and even make other, related requests before calling CouchDB. After the pre-hooks are processed, the proxy server initiates the HTTP request to the CouchDB server and fires any pending hooks. This allows the proxy server to keep track of open requests and deal with downstream server failures gracefully. Once the request to the downstream CouchDB server is complete, the proxy finish handlers are called. At this point, the response has not been sent back to the original caller, so it's possible to enforce any data access rules, remove any internal document fields, and otherwise clean up the response before it's sent. After the last finish handler has been run, the modified proxy response is sent back to the original HTTP client, and after the response is completely transmitted, the final handlers are called. This provides an opportunity to do any request cleanup, auditing, etc. To make a long video a little less long, I already wrote my own lightweight reverse proxy application server called Slipcover to implement this functionality. It's written in Python and uses the twisted event-based framework to run a standalone HTTP reverse proxy server. It's designed to connect to the local CouchDB server automatically and read its configuration from a special config document in a database named Slipcover. While there are a lot of configuration options related to setting up the HTTP listener service, the handlers key defines what hooks will be executed for each request. On server startup, each module named in the handlers list is loaded, and when a request comes in, the reverse proxy listener attempts to execute any handler functions that apply to the current request. Let's take a look at a very simple module that ships with Slipcover, the cores.py module. The first thing we notice is that there is only one function definition in the module, handle session URL. Remember the diagram that showed the various phases of the inbound HTTP request? This function is called for URLs that begin with /session, and when the request method is options, it modifies the response headers to include various cores-related values. Pretty simple, right? So let's look at another module, the card.py module. The card.py module is responsible for controlling access to the flashcards in the database. Let's look at the handle card put pre function. Looking at the function name, we can see that this function is called for all put requests to card resources before the CouchDB database is called. The next thing to note is that it uses the auth-only decorator, which was imported from the Slipcover sessions module. This decorator ensures that the current user has an authorized session and is logged in. Otherwise, it will throw an unauthorized 401 exception and the request won't complete. Once inside the function, we can see that it's trying to check if this document is new, meaning it has no unique ID, or else if the document already exists. If the document is new, it uses the Unix timestamp to allocate a new unique ID for it. Otherwise, if the document exists, it looks to see if the current user is authorized to modify it, either an administrator or the owner of that document. If not, it raises a forbidden 403 exception. This pseudocode is run for every request, with all qualifying handler functions being called, unless one of them throws an exception to terminate request processing early. So, for one hypothetical request to the FlipStream API, the 4 handler functions shown would be called in this order. By manipulating the order of the handler modules in the Slipcover config document and the specificity of the handler functions themselves, it's possible to come up with some pretty creative plugin handlers to solve common API issues. To find out more about Apache CouchDB, check out couchdb.org. And if you want to play with Slipcover, it's available on my GitHub page. It hasn't been battle tested, but if you find an issue, pull requests are welcome. This is the last video in this series about FlipStream. Thanks for watching. I'm planning to do a data architecture course that I'll be releasing on Teachable, which should be available by mid-October 2021. Be sure to contact me on LinkedIn if you have any questions, comments, or just want to talk shop.